Now we'll look at some examples and finding the area between bounding curves. So to start with, suppose I want to find the area between the curves y equals x squared and y equals square root of x. So let's first find it using vertical slices. And then second, we'll do that finding with horizontal slices. And here, when I'm talking about slices, of course, that's kind of referring to the Riemann sum. We want to find it exactly, so I do want to use an integral, but this is now telling me that I'm going to be integrating with respect to x. So you can think about we're cutting kind of perpendicular to the x-axis in order to get vertical slices. So what we can consider here is, first of all, I do need to know the relationship between these two graphs in order to decide which to subtract from the other. So if I think about a quick sketch here, we have y equals x squared. This looks something like this. And y equals the square root of x looks something like this. So this is y equals x squared. This is y equals square root of x. So certainly they intersect at the origin, but we also see that they intersect here. And that's going to happen at the value x equals 1. And that's also when y is equal to 1 in both cases. So from this picture, notice that if I'm thinking about vertical slices, certainly the function further away from the x-axis is y equals square root of x. So in terms of now finding the area of the region bounded between those two curves, I'm going to integrate the square root of x minus x against x. And to find the bounds in my integral, I focus on that x-axis and see that that region lies between x equals 0 and x equals 1. So here I can now anti-differentiate. So I'm going to get 2/3 x to the 3/2 minus, oops, I've lost my x squared there. So this should now be x cubed over 3. And we are evaluating this from 0 to 1. And so we're going to get 2/3 minus 1/3. Or 1/3. So the area of that region should be 1/3. Now, if I were to go back and now answer the same question, but with horizontal slices, again, that's another way of indicating that I want to slice perpendicular to the y-axis and therefore integrate with respect to y. Now, if I come back to my picture, again, what I need to think about is how these curves lie with respect to the now y-axis. So in this picture here, I'm going to think about cutting this way. Now, when we do that, what we should see here is that in this region, now the top function is going to be this y equals x squared function. However, we do need to think about the inverses here. So in this function, if y is equal to x squared, then we're going to say that x is equal to square root of y. Now, I don't have to think about plus or minus because I'm looking at the first quadrant here where both x and y are positive. And for this function up here, if y is equal to square root of x, then x is equal to y squared. So when I'm doing this second part, to be clear, I'm looking at these as functions of y, and the one that is further away from the y-axis is this one. So when I set up my integral down here, I have an integral, again, this is integrating dy. My function that is on the top with respect to the y-axis is the square root of y, and the one that is closer is in the blue box, x equals y squared. And my values for the integral are the y values, and that I see that ranges from 0 to 1. Now, it shouldn't be surprising, having set this up, that we get the exact same number, because we see that these two integrals, besides the variable name, are identical. I will point out that that is a coincidence for this particular example. So it's not always the case that the structure of that integral that you get looks the same. Now, it's not a coincidence that we got the same number. So, so you can think about that those, because that gives us the exact area, we should always get the same value for that area. But the fact that the setup looks exactly the same with different variables, that's not always going to be the case. So that's one example. Let's see, let me look at starting another page. For another example, maybe a slightly more complicated looking region. Suppose now that we want to find the area of the region bounded by y equals cosine of x and y equals sine of x from x equals 0 to x equals pi over 3. So let's think about that region. So again, we're in the first quadrant. Whoops. Try that again. So we're in the first quadrant and we are looking at sine and cosine. So in terms of trying to think of this picture, we're going to have that to start with, cosine is going to be, so maybe let's look at, so we've to pi over 3. Let's think about the graph at maybe till pi over 2. So cosine would look like this, and sine, if we were going to draw that, would look, oops, should go back up to 1. So like this. Now, in terms of looking at this graph, like I said, this is pi over 2. So let's place pi over 3 somewhere here. I know where they intersect. It's not really drawn perfectly to scale. They intersect at the value pi over 4. So when we're looking at this graph, notice what happens. Maybe let me label these. Let's let this be blue. This is my cosine of x, and this is sine of x. So first of all, I'll point out, given that we get to choose whether we integrate with respect to x or with respect to y, I'm going to choose to integrate with respect to x, because doing that with y would involve several problems, but one of those is we'd have to take arc sine and arc cosine. But here, what we can do is keep it in terms of x, but something happens at this point. In particular, the function that was originally on top, cosine, now becomes the function that's on the bottom. So what we have to do here is really split this up into two integrals. So we have, for one, the integral from 0 to pi over 4. That can give us the area up to this pig dot. And then I want to add to that the area between pi over 4 and pi over 3. And like I said, that's because we're crossing over there. So with that in mind, now I'm going to know how to set this up. And notice that the picture helped, because I could really see that I did have to do that. And again, pay attention to which function is further away from the x-axis. So the area, I'm going to take, first of all, the integral from 0 to pi over 4, where those two curves intersect. And on that interval, we take cosine minus sine. And then I'm going to add that to the integral from pi over 4 to pi over 3. And on that interval, we take sine x minus cosine x as our integrand. So this is our setup. Now beyond this, we're just going to antidifferentiate. So we want to remember that cosine has the antiderivative of sine, and minus sine has antiderivative positive cosine. So this is evaluated from 0 to pi over 4. And we're adding to that, the antiderivative of sine is minus cosine. And the antiderivative of minus cosine is minus sine. And this is evaluated from pi over 4 up to pi over 3. Okay, so all of these are kind of major angles. What we can think of is both sine and cosine evaluate to 1 over root 2 when you plug in pi over 4. And we're subtracting what we get when we plug in 0. Sine of 0 is 0, cosine of 0 is 1. So that's the first integral. And then now, looking at the second, when we plug in pi over 3 to cosine, that's where cosine evaluates to 1/2. So this is minus 1/2. Sine of pi over 3 is root 3 over 2. So we subtract root 3 over 2. And now we already looked at the values at pi over 4. In this case, these are both being negative values. Okay, so that's what we get. We can clean this up a little bit. In particular, notice that we have, these end up, if you distribute this minus sign, these are all positive. So we're going to get 4 of those. So let's see, we're going to get 4 over square root of 2, which you could also write as 2 square root of 2. And then collecting what's left, so I have a negative 1/2, and I have a negative 1. So we're going to have minus 3/2, and we have minus square root of 3 over 2. So this is going to be the area that we end up with here. But again, it was very helpful and really important to sketch the graph. So I would really recommend that for any kind of applications where we're looking at area between bounding curves, to make sure that the region is clear, to make sure that the values for the limits of integration, that's clear, and also to decide which function is subtracted from which. And we can see here that it might not be consistent over the entire interval.